Hello again, chemistry students, and welcome to another lesson on electrochemistry. What we're going to talk about in this lesson is an idea referred to as the Nernst equation, and this is named for a chemist named Walther Ernest Nernst. And let's remind ourselves what we've done in terms of electrochemistry and doing things like calculating cell potentials up to this point. So I'm going to start going through and filling in the blanks here. All right. It should be clear that the standard reduction potentials that we've been talking about, right, those that are on that standard reduction potential chart, right, they are values that are done under standard conditions, right? So the reduction of, say, copper 2 to copper is 0.34 volts, and that is assuming a particular set of conditions, right? What are those conditions? Those conditions are meaning that the temperature is going to be 25 degrees Celsius, right, standard state temperature, and that the reactants have a concentration of 1 molar, or if they're gases, they're present at 1 atm. All right, so that's our typical thermodynamic standard state conditions. Now, of course, not all galvanic cells are going to be operating at these specific conditions. And so if I want to figure out what the cell potential of a galvanic cell that might be running at, say, I don't know, a warm day of, 35 degrees Celsius, or a cold day of 5 degrees Celsius, or maybe the concentrations inside of my galvanic cell are not 1 molar, maybe they're 0.05 molar, maybe they're 2.5 molar. In order to evaluate the cell potential at these different non-standard state conditions, we're going to need the Nernst equation. All right, so let's continue filling in the information here. To derive the Nernst equation, let's start off with our delta G and E relationship that you saw in a previous video about connections between thermodynamics and electrochemistry. So you'll recall from that video that we had an equation that looked like the delta G0 is equal to minus the moles of electrons that are transferred times Faraday's constant, 96,485 coulombs per mole of electrons, times the standard cell potential, right? So this is an important connection. It reminded us, or it told us, that cell potential is really just a version of free energy. It's the amount of free energy that is exchanged per charge. It's the amount of work that an electrochemical cell can do per charge that is passed. All right. Now, we, of course, could have the non-standard state conditions of this very same equation, which we're just dropping the superscript zeros, okay? And this is going to bring back another connection to thermodynamics. I need to remind you of an equation we learned when we were doing thermodynamics, specifically that the non-standard free energy change, the delta G without the superscript 0, is equal to the standard change of the delta G, plus we had what we often refer to as sort of a thermodynamic correction factor, plus RT times the ln of Q. So just to remind you, right, so this is a non-standard free energy change. This is the free energy change that we chemists or chemical engineers could establish for our reaction once we knew what the standard free energy change was, what was the sort of inherent amount of work that was tied up inside of a particular reaction. And then depending upon the temperature at which we do the process at and the natural log of Q, remember here Q is the reaction quotient, it's the products over reactants raised to the power of their balancing coefficients, but you're not yet at the equilibrium conditions, right? So this is the non-equilibrium version of the mass action expression. All right, so now if I take these various equations that we are putting together and start to do some substituting, then I could plug in my delta G and my delta G zeros that I've got from the above equations and plug them into this thermodynamic equation to write that minus NFE, all under non-standard state conditions, is equal to minus NFE0, our standard state connection, plus that RT ln Q again, ln Q. All right, now I'm going to rearrange and solve for E for my non-standard state cell potential. And when I do that, I'll have the standard cell potential, the one we can get from the various reduction potential charts we've been playing with, minus the gas constant, temperature divided by the moles of electrons transferred, Faraday's constant, and the natural log of Q. So this is a biggie. This is an important equation, right? This is the Nernst equation that we have here. All right, now if we do a little bit of rearranging and a little bit of combining, we can actually simplify the Nernst equation to a version just below it right here. This is another version of the Nernst equation. So if I take the gas constant, 8.314, the temperature, of course, in Kelvin, divide it by the moles of electrons for a given reaction times F, if I essentially take this collection, let me go ahead and circle it, box it in. If I take this collection of constants at specifically 25 degrees, then I get that version of the Nernst equation. It's a little bit simpler to work with in terms of the number of things you have to plug into your calculator. But it's important to keep in mind this only works if you're at specifically 25 degrees. If you're at any other temperature, then you're going to have to work with the sort of full-blown version of the Nernst equation. So again, let's be clear about what we have here. If I know the standard cell potential of a galvanic cell, and I know the specifics of the conditions I'm operating at, the non-25 degree temperature, whatever I might want to plug in here, and the various concentrations or pressures here for Q, I can find a non-standard state cell potential. Okay, so let's take a look at a specific example here. So I have this galvanic cell on the right here where I have aluminum and aluminum 3 and copper 2. And so I want to go ahead and see if I can figure out what the cell potential for this galvanic cell would be if I have non-standard state conditions, right? I'm no longer at 1 molar. I'm at 0.01 molar for the aluminum and 1.4 molar for the copper. So the first thing you're going to want to do here is write out what the overall redox reaction is that's going on in this galvanic cell. And of course, we need to combine the two half reactions in such a way that you get a positive potential. By definition, a galvanic cell is spontaneous, so it has a positive potential. So to get the right sign for the potential, what we're going to do is we're going to go ahead and reduce the copper 2. So I'll have 3 copper 2s that are reacting with 2 solid aluminums. Forgive me for not putting in my phase labels. And that would go ahead and turn into 3 solid coppers and 2 aluminum plus 3. All right, so when I combine the half reactions in this way, my overall standard cell potential, my E0, is going to be 0.34 for the reduction of the copper 2. And then I have to flip the sign for the reduction of aluminum 3 to aluminum, because here, right, we're doing aluminum and oxidizing it to aluminum 3. So then my potential for that oxidation half reaction is 1.66 volts. So my overall standard cell potential is 2 volts. So this is already pretty good. This is a pretty powerful battery in terms of the amount of electrical work it could do. But let's go ahead and plug in what the result would be if I were working under these non-standard state conditions. So let's use the Nernst equation. So we're going to have then E is going to be equal to E0, which in this case is 2 volts, minus, and I'm going to go ahead and use the full version of the Nernst equation. We are at 25 degrees, so I could get away with using the simpler one, and I'm going to use the simpler one later. I just want you to see an example of where we use the full-blown version. All right, so then I have to plug in R, which is 8.314, times the temperature, which is 25 degrees, or 298 Kelvin. Divide that by, now, this is always the tricky part when it comes to the Nernst equation. How many electrons are being moved around in this redox reaction? Well, I've got copper 2 going to elemental copper. So that's 2 electrons, but I'm doing it 3 times. So that's clearly 6 electrons. Or I've got aluminum 0 going to aluminum 3, but I do that twice, that 2. is 6 electrons. So clearly one way or the other, I've got 6 electrons. And of course, in a balanced redox reaction, how many electrons come out of the oxidation, that number of electrons also goes into the reduction. So I'm going to divide this by 6 and then multiply it by Faraday's constant, 96,485 coulombs. Now we need to multiply this by the natural log of the reaction quotient. And so we see that aluminum 3 is a product, so that's going to go in my numerator, and that was a value of 0.010 molar, and I'm going to need to go ahead and square that, divided by the 1.4 molar for the copper 2, and I'm going to need to cube that. All right, so common sources of mistakes: not raising the concentrations to the appropriate balancing coefficient in the overall redox reaction. Now at this point, it's a calculator thing, and I would definitely make sure I practice these problems, because you want to make sure you and your calculator are on speaking terms when it comes to doing these things through. I tend to kind of go from back to forwards. I do this part of the calculation, take the natural log, do the multiplication, do the division, hit the plus minus sign on my calculator, and go ahead and add the standard cell potential. All right, so if you and your calculator can work through this, you're going to see that the new cell potential we get here is 2.04 volts. Now, that's not a big change, right? We went from 2 volts to 2.04 volts. But in every portion of a volt, there's actually a fair amount of work that's going on here. So while this only changed by 4/100ths of a volt, that actually does represent a fair amount of work that the electrochemical cell could do. All right, let's move on. So, as it says at the top here, one of the most common questions, and I alluded to this before, is students can sometimes have a little bit of trouble figuring out the value of n. So let's talk about how much the value of n really doesn't change doing the calculation. Of course, you have to have the correct version of n, but I'm going to show you here, you can actually do the calculation. So long as the redox reaction is balanced, you can pretty much do it with any version of n. So for example, on the left-hand side here, I have that same reaction we were just playing with, balanced the way that you saw me balance it, and we learned there that the value of n for that version of the equation was 6, right? We had 6 electrons. Now on the right-hand side, I've balanced the same redox equation, but in a slightly different way. And so now the value of n here is aluminum to aluminum 3. There's only one of them. So that's a value of 3 for n. All right. Now, if I go through and I use the Nernst equation, now we already know that on the left-hand side, if I use 6, we saw that the voltage was 2.04 volts. Now, I'm going to redo the Nernst equation now for this version where we have 3 electrons, and let's see if we get the same answer. And I'm going to use the shorter, more compact version of the Nernst equation. So on the right-hand side here, then, my standard cell potential, or my non-standard cell potential, E is still going to be equal to 2 volts for the standard cell potential. Now minus, using the shorter version of the Nernst equation, because I'll assume that I'm at 25 degrees still. Now divided by n, which in this case is 3. That's 3 times the natural log of, so I have, if I use the same concentration as before, 0.010. Now that's just raised to the first power based on the way I balanced this equation, right? So there's only 1 mole of aluminum, so I'm going to leave that as raised to the 1 to the first power, divided by 1.4. And I'm going to raise that to the 3/2 power. Now, go ahead and do this with your calculator yourself, and you should definitively see that the cell potential here is going to be still 2.04 volts. Okay, so long as the reaction is balanced in one way or the other, it doesn't really matter what the coefficients are, so you should of course be getting the same cell potential. The only difference being, are you dividing here by 3 electrons for this way we balanced it, or 6 electrons for that way we balanced it. Okay, just again make sure you have a balanced redox reaction. Okay, and then this brings us to one more topic that we can talk about for this video, and this is the idea of a concentration cell. A concentration cell is a galvanic cell, except in both the anode and the cathode, we have the exact same ingredients. But we're still able to get a positive potential because the concentrations in those two compartments, in the anode and the cathode, will be intentionally set up to be different. And that difference in concentration, that sort of concentration gradient, if you will actually create a noticeable, albeit small, cell potential difference across the two compartments of the galvanic cell. So what we're going to do here is we're going to look at a concentration cell that is built using solutions of copper. So if we look over here, I have a copper electrode in a solution of copper 2, a copper electrode in a solution of copper 2. All right. The only difference I'm going to have here is one of the compartments will have a solution concentration of 0.001 molar copper 2. The other one will have a concentration of 1.4 molar copper 2. All right. So now, in order to figure out what's going on here, let's first write out the chemistry here. Right? We are going to be doing the exact same chemistry on both sides. So in other words, I'm going to have copper 2 plus reacting with elemental copper to form elemental copper and copper 2 plus. Okay? So I'm just kind of going around in a circle, as it were. But the important thing is that the copper 2 that's going to be on one side of the galvanic cell, its concentration is going to be different than the copper 2 that's on the other side of the galvanic cell. So let me zero in on the cell here for a moment. So let's do what we kind of typically do, or at least what I typically do. And whenever I build a galvanic cell, I have a tendency to put the anode compartment on the left and the cathode compartment on the right. I do that because it also kind of works with line notation. If you remember from a previous video, in line notation, you always kind of write the anode reaction on the left side and then the cathode reaction on the right. All right, so you'll remember I've got the two concentrations of 0.001 molar and the concentration of 1.4 molar for my two copper solutions. The question is, in the anode compartment, am I putting in the more dilute concentration of copper 2 or the more concentrated amount of copper 2? Well, if you think about it kind of, and I don't want to use the term too much here, but in a chemistry common sense, the compartment that has the less concentrated, the more dilute copper 2 solution, well, that copper 2 solution is going to have to eventually try to equate the concentration in the other compartment. So the more dilute solution will be in the anode compartment. So I'm going to put the concentration of 0.0010 in the anode compartment. And then I'm going to put the concentration of 1.4 molar in the cathode compartment, because what's going to happen as the electrons travel through the external circuit, right, the fact that the left-hand side is being oxidized means that more of the solid copper will get oxidized and increase this concentration of copper 2 as the galvanic cell operates. And as the electrons end up here, it's going to take the copper 2 ions in solution and reduce them and form elemental copper, so this concentration will go down. And you can see where this is headed. Eventually the galvanic cell, this concentration galvanic cell, will stop working when the concentrations in both compartments are the same. Okay? All right, so let me zoom back out and go ahead and do a calculation here. So what is the value of E0 for this cell, or really any concentration cell, right? What is the E0? Well, again, just think about what's going on here. We are reducing copper and we're oxidizing copper. So we're again kind of chasing ourselves in a circle. If we were at standard state conditions, the E0 here for at least the copper, the specific numbers would be 0.34 minus 0.34. So for any concentration cell, my standard cell potential, right, the standard cell potential is 0 volts. A standard state concentration cell doesn't do anything. But if we go ahead and work with the concentrations 0.001 and 1.4, then using the Nernst equation, we can see that we're going to get actually a positive potential. So 0.00 volts minus, and I'll use the short version of the Nernst equation here and assume we're at 25 degrees. I'm exchanging 2 electrons times the natural log of. Okay, so what I want to make sure that I do is I want to make sure that the lower concentration, the more dilute solution, is on the product side, and the more concentrated solution is on the reactant side, because this is the concentration that has to be reduced. This is the concentration that has to be oxidized. So this is going down, this is going up. And so that means I will put the 0.0010 molar in the numerator, the 1.4 molar in the denominator. All right, and then this makes some mathematical sense, right? This ratio is going to be less than 1. The natural log of a number less than 1 is going to be negative. Combined with that minus sign means the overall galvanic cell potential is going to be positive. Now, prepare yourself. It's not really a big number. It's only 0.09 volts to 2 decimal places. So it's not like I'm getting a lot of voltage. But again, voltage can do a lot of work. So there's something here. There's something here we can work with, even if it isn't a whole heck of a lot. All right. And then down here at the bottom, it just it says that again. All right. We go through all this trouble to calculate a very small potential, but even though it's small, there's a lot of practical purposes here. pH meters are actually based on a concentration cell setup, and biological systems, when you have a concentration gradient across the membrane, that small difference in concentration can lead to important electrochemical potential across the membrane. All right, so that should do it. That's the Nernst equation. So it allows us to find the cell potential for a galvanic cell. Remember, that's always going to be positive under any condition that we chemists or chemical engineers can create in the laboratory. And then using the Nernst equation, we're able to understand the phenomenon of concentration cells that allows us to have the same ingredients on both the anode and cathode sides and create a little bit of potential by way of a concentration difference. All right, that'll do it.